Enthalpy of neutralization is one of 3 enthalpy changes you're supposed to know about in detail in the higher course. It's probably the trickiest of the 3 because unlike the other 2, enthalpy of combustion and enthalpy of solution, this one is concerned more about the product than the reactant, the product being water. Enthalpy of neutralization is really the energy that's produced when 1 mole of water is formed during an acid-alkali reaction. Okay, so once again, let's repeat that. The enthalpy of neutralization is the energy change when 1 mole of water is produced during an acid-alkali reaction. In practice, how could you find that value? You could put acid and alkali in separate insulated beakers to avoid heat loss. Let's suppose we did something like this. We take hydrochloric acid, not necessarily 1 mole, something far less. We take hydrochloric acid and sodium hydroxide and put them in these beakers. Let's suppose we have 25 cubic centimetres of each solution. Let's suppose they're both 2 moles per litre. That's the concentration, 2 moles per litre. Prior to mixing, you would have to find the temperature of each one. Let's suppose, for example, that the temperature of the acid is, say, 21 degrees Celsius and the alkali 23 degrees Celsius. What do we take as our starting temperature? Well, obviously, the average. So the average initial temperature will be 22 degrees Celsius. Now we mix them together. When we mix the acid with the alkali, heat will be produced, the solutions will get warmer. And not only that, there won't be 25 cubic centimetres in each separate beaker, there'll be 50 cubic centimetres in all. Let's say the temperature went from an average of 22 degrees Celsius to a final temperature of 33 degrees Celsius. That's a temperature rise of 11 degrees. Can we use these numbers to calculate the enthalpy change involved? Here we go. It's the same old equation. The energy produced equals Cm delta T. C, that's the specific capacity of water, is the only number we can use. I know these are not pure water, but there's no other number available. So 4.18. M, now be careful. M is the mass of liquid that the heat's in, and the heat is now in a grand total of 50 cubic centimetres, which is the same as 50 grams, which is the same as 0.05 kilograms. So, the mass of liquid is 0.05 of a kilogram, and the temperature change was 22 degrees. No, it wasn't. The temperature change, it was 11 degrees, a temperature rise of 11 degrees. So, how much energy has been produced in this small scale reaction? And the answer, of course, is not a great deal. 2.3 kilojoules. But the question is, how much water was made in this reaction? After all, we will need to work out the energy change if a mole of water had been used. Well, here we go. Can we calculate how much water was formed? We started with hydrochloric acid and sodium hydroxide. How much acid did we start with? We can use the little formula N equals CV to find out. The concentration of the acid we said was 2, and the volume of acid was only 25 cubic centimetres, which out of 1,000 means we didn't start with a great deal of acid. There, 2 times 25 over 1,000 is 0.05 of a mole. We use the same quantity of alkali, the same concentration, the same volume, therefore the same number of moles, 0.05 of a mole of alkali. Now, when we look at this acid-alkali reaction, 1 mole of acid and 1 mole of alkali will produce 1 mole of water. It follows, therefore, that if we're using these quantities of acid and alkali, then that's how much water was made in this small scale experiment. So we did not make a mole of water, we made only 0.05 moles of water. But we do know that in making this quantity of water, this amount of heat was involved. So we can say that 0.05 moles of water involved 2.3 kilojoules of energy. If we'd done it on a mole scale and produced 1 mole of water, the question is, how much energy would that have involved? This is going to be a much larger amount of energy, so we want to scale this number up. Scale it up by putting the larger number on top and the smaller number below. And if we do the sum, we'll find it comes to 46 kilojoules. Now, we need to tidy up this answer. First of all, we can say it's 46 kilojoules per mole. And it's per mole because now it is related to 1 mole of water. And secondly, and very importantly, we must put in the negative sign. The temperature went up, it's an exothermic reaction. And finally, how does this compare with a data book value? This is a data book value not in your data book. You'll find the data book says it should have been about 57 kilojoules per mole. Why the difference? Possibilities are heat loss. It's very hard to avoid some heat escaping from the system. And possibly the fact that we had to use an average temperature to begin with will be an error that was unavoidable. That is entropy of neutralization.